All right, folks, we're going to finish off our introduction to antidifferentiation with two what they call initial value questions. And so we're told that the derivative of a function is equal to the square root of x. And then we'll talk about this information as well, and I'll do my best to draw a picture of the question. But they're basically saying, what's the function that satisfies both of these criteria? Well, so when you're solving for a function, sometimes it's called y equals. So I kind of like to look at this like it's an algebra question. Let's start with this initial relationship they give us. If I was going to think like an algebra person and solve that for y, I'd first of all say, well, let's clear the fraction, so to speak, by multiplying both sides by dx, and that would leave dy over here. And then, while we're at it, because there's going to be some calculus coming up, let's change that square root of x into x to the 1/2 power. Okay? So, kind of an algebra idea. Clear the fraction, so to speak. All right? Now, how do you change a dy into a y? Because we're supposed to find the function that satisfies all this. Well, this is new to us, but the inverse, that's like a differential idea. And how about antiderivative? So the idea would be, why don't we integrate both sides of this? Okay. You can do that to both sides just like anything else. Now think about it. That's like a 1 in there. So what's the integral of 1 with respect to y? Y, exactly. Now, there is the plus a constant here. And I guess I'll put it in here. Plus c. And we'll talk about, let's just trust that idea for now. Okay. Now, if we go to the other side and integrate this one with respect to x, we would do the power rule on that one. And so once again, that power rule applied to that one would be, again, n plus 1 over n plus 1. And so 1/2 plus 1 is 3/2. And then over 3/2 is the same thing as times 2/3. So I want you to get used to that invert and multiply whenever it's appropriate. And yes, this one would also have a constant. Now the thing is, the constant over here and the constant over here don't have to be the same thing. So we could have a C1 and a C2. But what I would just recommend doing, and we'll do this on the second one that we'll enjoy in a bit, is if both sides have a constant, why don't we move this one over there and combine it with that one? And so when you combine whatever this constant is with whatever that constant is by subtracting it over, wouldn't this just become a singular constant? Let's combine the two constants on the two sides of the equation into a single constant over there on the other side. Okay, so y equals 2/3 x to the 3/2 power plus c. So here's what I like to think about. That c could be a variety of different numbers. We talked about that constant on the end. And so the quick picture I just would suggest, and this doesn't have to be perfect, but the idea is that if c were to be 0, for example, then we could graph that thing, wouldn't we? And whatever that graph looks like is somewhat immaterial, so I'm just making something up. So suppose, this is the graph of that when c equals 0. Okay? It's not, but pretend. It doesn't matter that it be perfect. So that's an example of that. And so the idea would be that depending upon the different values of c, for example, if c happened to be a 1, wouldn't that be the curve that's 1 unit above this one? And so whatever that base curve is, in my mind, that corresponds to c equals 0, if you just moved every point on that base curve up 1 unit, that would equal c equal 1, wouldn't it? And then if c equaled negative numbers, they'd be down here, wouldn't they? So just, it bumps it up and down depending upon the different values of c. I hope that made sense. Okay? And so here's the idea now. We need to talk about this information. Of all the curves for all the different values of c, the question is, find the one that satisfies that information there. Now, they gave it to us in a kind of strange way, but I'd like to point out to you that what they're saying is that when x gets replaced with 4, y ends up equaling 1/3. So in other words, that's an ordered pair there. Okay? And so if we were to invoke that, I don't know if invoke is the right word, if we were to interject that into the discussion, so they're basically saying of all these curves over here, which one passes through the ordered pair 4, 1/3? What does the C value have to be for that curve to hit that point? That's another way of perhaps saying it in a better way. So, what do? Well, you take this and you go, all right, this would be true for all curves. Now let's see which of those curves would satisfy that information. Y is 1/3. X is 4. What does C have to equal? Okay, so basically you stick that ordered pair into this thing. And then you do arithmetic and solve for C, which now you'll have fun making fun of me. So let's see, 4 to the 3/2 power, I believe would be 8. Is that right? Yeah, 8. Yeah, 8. And then 8 times 2/3 would be 16/3. And then we subtract over the 16/3. And the C value, when we plug that ordered pair in, would be -15/3, otherwise known as -5. So that's the C value. All right, so to finally give an answer here, the function that satisfies both of these criterion would be, let's see, now I'm going to pop back up and put -5 in there. So the final answer to all this would be the graph, the curve, y equals 2/3 x to the 3/2 plus -5, otherwise known as -5. Okay, so the way that relates back to this picture would be this. If you had the base curve for when c equals 0, and then you had -5 tacked on the end, that would be the curve 5 units below that one, right? Whatever the base curve was. So I'm just trying to draw this kind of a parallel looking curve with c equals -5. And the idea would be that that is the particular curve that passes through the ordered pair 4, 1/3. All right, of all the curves, c had to equal -5 for it to hit that point 4, 1/3. Woo! All right, I said we do 2 of them. I think we're going to pause there, and we'll do the second one here in a moment. So again, that would be an example of an initial value question. Let's go antiderivatives.